My presentation is entitled Optics, Ceramics, Glass, Solar Cell. Welcome to this course on optics, ceramics, glass, and solar cells. I am excited to present this useful and practical journey. Let's dive in. Welcome to today's session on microelectronics packaging. We'll explore metal nanoparticle pastes, a key conductive paste technique used to form electronic components like circuits, electrodes, resistors, and dielectrics. Unlike conventional thick-film pastes, which use micrometer-sized metal powders and organics, nanoparticle pastes offer cutting-edge precision and performance. Let's dive into this innovative technology. Today, we'll look at how conductive pastes shape electronic circuits. Using a screen printing or dispensing, pastes are applied to substrates, then dried and fired to remove organic additives like dispersants, fusing metal particles into conductive thin films. Conventional pastes, however, require firing above 550 degrees C, limiting use to glass and ceramic substrates. Enter metal nanoparticle pastes. With particle size from a few to tens of nanometers, these enable smaller, flexible components. Smaller particles mean higher surface energy, so they are capped with organic groups to control growth and size, revolutionizing microelectronics. Let's explore this game changer. Here we examine gold nanoparticle pastes for circuit formation. The TEM image reveals monodispersed gold nanoparticles averaging under 10 nanometers perfectly dispersed for conductive pastes. This uniformity ensures high-quality paste performance. The figure also illustrates how these pastes form precise circuit patterns, leveraging their nanoscale properties for enhanced conductivity and flexibility. Let's take a look at this cutting-edge approach. Like traditional conductive pastes, metal nanoparticle pastes are heated to decompose organic protecting groups and components, forming conductive thin films. But here's the game changer. Due to the quantum size effect, nanoparticles fuse below 300 degrees C, enabling circuit patterns on plastic, glass, and ceramic substrates. They also allow fine patterns with lines under 50 micrometers via screen printing, overcoming limitations of conventional thick films paste. Looking ahead, we are targeting 10 micrometers lines and leveraging nanoparticle dispersion for inkjet printing's ultra-fine patterns. Plus, nanoparticles are now used as joining materials, making them a rising star in microelectronics packaging. Let's explore their potential. Here, we are exploring the application of Raman scattering in chemical analysis. Raman scattering, or the Raman effect, discovered by Sir Raman, is the inelastic scattering of photons by molecules or atoms. When light interacts with a material, most photons scatter elastically, called Rayleigh scattering, keeping the same energy and wavelengths as the incident light. However, a small fraction scatters inelastically, shifting energy due to molecular transitions, which we call the Raman effect. This is key in gases, where energy changes reveal molecular properties. In chemical analysis, we focus on this transitional Raman effect to study molecular structures. Excitingly, when electromagnetic radiation interacts with the surface plasmons, it can enhance Raman scattering intensity, especially in semiconductors, boosting our ability to detect and analyze chemicals with precision. But how this powerful technique transforms chemical analysis? Today, we are examining a silicon solar cell as shown in this schematic. At its core, we have the P material forming the base, which meets the N layer at the PN junction, where the magic of charge separation happens. On the P side, an evaporated aluminum dot serves as a contact, efficiently collecting positive charge carriers. On the N layer, an evaporated gold contact gathers negative carriers, completing the circuit. This design harnesses sunlight to generate electricity with precision. Let's explore how these components work together to power our world.